Let's begin with the question number one. The question is asking us a 960 Newton block is suspended as shown on, or the beam AB is weightless and is hinged to the wall at A. Over here, it is hinged. Alright, so we are going to find the tension, magnitude of the tension at BC cable. Okay, so what is a BC? So here is B. So here we are going to find it here. Okay, as you see here, basically this is, we are going to apply the Pythagoras over here, okay? Pythagoras theorem to find the tension force, okay? So tension force will be equal to the components, the x squared plus ty squared, okay? We're going to apply the Pythagoras to find the tension force in CB. So here, before finding Pythagoras, let's find our angle, okay? Theta, okay? So let's find the theta. So how can we find the cos theta? Cos theta from the triangle. How? It is going to be
y over
since here is 3, here is 4, what is going to be over here? It is 90 degrees, by the way. So here is going to be 5, special angle, okay? So we are going to divide 4 to 5 to find the cos theta. Since we don't know theta, we are going to change the places. So cos 4.5 is going to be equal to theta. So here theta will be 37 degrees, okay? So here it's going to be 37 degrees. So then, second of all, let's check for vertical and horizontal component. What kind of component is this? This is our, the weight is going to be our vertical component. So what about our horizontal component? We don't know anything about our horizontal component over here. That's pretty this way actually. This for Tx. So to find the Tx, we are gonna use this one. We're gonna use Ty times cos theta over sin theta. Okay? Cos theta over sin theta will give us our Tx. Why? Because we don't know anything about Tx, so we have to apply this in order to get the Tx over here. So we know the Ty is 960. So let's put them here. Let's put them over here. T equal 960 times cos 37 over sine 37 square of this plus what we have 960 square, right? So when we apply this, we're going to get the t over here. As you see, 900, you can take the common parenthesis of 960. 960 will come over here, okay? And here, we are going to multiply, we are going to get from the other part 1.667. So we're going to get around 1,600. You can just apply it. I'm not going to go further. So here, we're going to find 1,600 Newton dash of the T, okay? So the T will be 1,600 Newton, okay? Any questions? An 80 Newton uniform plank leans against a frictionless wall as shown. The magnitude of the torque at point P. Here, we're going to find the torque. So in order to find the torque, let's put our weight in the middle of the plank, okay? So what kind of component we have over here? We are going to have here mg cos theta, right? And this part is going to be mg sin theta, but we don't need mg sin theta. We are just going to need mg cos theta over here, okay? So to find the cos theta, first of all, let's find the cos theta again here, the theta. How can we find the cos theta? Again, adjacent over hypotenuse is going to give us cos theta, adjacent over hypotenuse, adjacent over hypotenuse. So cos theta will be 3 over 5, right? Which is going to be 0. Which is going to be like theta. Here again, cos 3 over 5. That is going to be 0.6, so theta will be 37, 53 degrees. 53 degrees. The value of cos 53 is going to be 0.6. So we find the theta. Now second step, let's find the total torque. Let's apply the second law of equilibrium. Total torque must be 0, right? So here, what we have, mg cos theta. Here the distance was the L, right? But since we take the weight in the middle of the flag, so it's going to be L over 2, right? So that is going to be equal to, let's write what we have over here. You know that mg, the value of mg is 80. Our cos here is cos 37. What is the value of cos 37? Cos 53, sorry. 0.6 times 5 over 2. Okay, so 80 times 0.6 times 2.5. When you multiply this, you're going to get 120 Newton, the answer of the torque around the P point P. Okay, that's right. So the torque around point P will be 120 Newton. So since we are looking just for the torque over here around P, that's why we just apply the cos theta. Okay. Here there is an 800 Newton man stand halfway up a 5-meter long ladder of negligible weight. The weight is negligible. That means we don't care about the ladder's weight. The base of the ladder is 3 meters from the wall, assuming that the wall ladder contact is frictionless. So the wall pushes against the ladder with a force of magnitude. So we're gonna find the force over here. So okay, so let's draw the force diagram over here. Okay, so what kind of force do we have? We have force here due to man, which is 800 Newton. Here we have the force due to wall, right? Okay, so let's just apply it here. Since we don't care about the other stuff, there is no friction. So let's just do this. Here is going to be 4 meters, by the way. There is 4 meter distance over here. The ladder since here is 5 meters from the special angle, special triangle. We can say there is 3, 4, and 5 triangle. So what's going to happen now? So this part times this is going to be equal to this part times half of this part, okay? Half of the ground part. So it's going to be like this. 4 times n will be equal to mg times 1.5, half of the distance of the ground, okay? This part. So then let's put it here. 4n equal to, or mg is 800 times 1.5. Let's divide both parts by 4, so it's going to be 800 times, sorry, this is 4. So you can simplify them. 800 over 4 is going to be 200. Then 205 times 1.5, that is going to be 300 Newton. So the force due to wall applies on the ladder is going to be 300 Newton. Okay? 300 Newton. A 240 Newton weight is hung from 2 ropes as shown. What is the tension force of the horizontal rope? So we're going to find the tension force here. Let's call this one TH, okay? Tension force H. But over here we have distance. Let's call it L. Here we are going to have, let's continue. Let's make it like this. Here we're going to have L times sine theta. Here we're going to have L times cos theta. Okay, so let's apply the formula. Here we have weight, of course. So weight times the vertical components L times cos theta equal to th times L times sine theta. Okay. So then the LL, as you see over here, they're gonna cancel out each other. So we're gonna have here, we are looking for TH, so let's leave alone the TH. TH is gonna be equal to omega W times cos theta over sine theta. Okay. So we know that cosine over sine theta is going to be tangent theta, but we don't need to do that actually. Let's just put what we have over here. So it's 240 times cos 30 over sine 30. The theta is 30 degrees. So here we are going to get RTH around 460 Newton. Okay. So the horizontal tension in the horizontal part will be around 416 Newton. Okay. The uniform ladder of length weight 50 Newton. Okay. The weight over here is 50 Newton. We have force due to wall and W, let's call it. We have normal force over here. Let's call it NF. Okay. And we have friction force in this direction, which is friction force. Let's call it FF. Okay. And here we have theta. So uniform ladder, the length and weight 50 Newton rest against a smooth vertical wall if the coefficient of static friction between ladder and the ground I think it's given you, we don't know about that actually. So let's apply the first and second law of the equilibrium. That's first law of equilibrium. What does this tell us? It tells us the total force must be zero, right? In the x direction, we are gonna have, in the horizontal direction, we are gonna have friction force minus the force from the wall. That is going to be equal to zero. This is the first equation. Okay? The second equation, the total vertical component, the force of the vertical component must be zero. So what we have there? We have force due to the ground over here, the normal force, and we have the weight of the object, which is going to be zero. This is the second equation. So here you can say friction force is equal to here, like for example, friction force will be equal to the normal force from the wall. And here you can say that normal force will be equal to weight. Okay? These are the equations that we are going to use later on. So let's apply the second condition of equilibrium. What the second condition of equilibrium tells us? So second condition of equilibrium, what does it tell us? It tells us that the total torque must be zero, right? The total torque must be zero. So let's apply the torque, clockwise torque for first of all. Clockwise torque. What is clockwise torque? Clockwise torque is going to be L over 2. Remember, the clockwise is going to be the direction of like this direction will be clockwise, okay? And this direction will be anti-clockwise. So L over 2 times mg times cos theta. That is going to be clockwise torque. And then let's find the anti-clockwise torque, which is going to be, again, L times mg times, or let's say normal force due to wall times sine theta. Okay? This is going to be anti-clockwise torque. So now let's make them equal, these two equations, because the total torque must be zero. So let's write here, let's make it equal, these two equations. So let's write it here, L over 2 times mg cos theta equal to L times force on the wall times sine theta. Okay? So these L's are going to simplify themselves. So let's move on, let's move forward. We said that the force on the wall over here, let's go to the other page, over there. So let me write the last equation. Yes. All right. So let's write the last equation that we find for the torque part. L over 2 times cos theta times mg equal to L times force on the wall times sine theta. Again, the L's are going to simplify themselves. So here, Let's go to the first part, condition of the equilibrium part. We found out that the force of the wall is equal to friction force, right? The one. So now we can replace this part, okay? We can replace it. And let's put the sine theta and cos theta over here. Sine theta and cos theta. You can just send it over here. So sine 1 over 2 times cos theta over, let's wait, this 1 over 2 times mg, okay, over, let's send this one underside of the equation. It's going to be no force on the wall equal to cos theta over sine theta. Sorry, sine theta over cos theta. What does sine theta over cos theta mean? Sine theta over cos theta.
Tan theta.
What does this mean? It means tangent theta, right? So we can put it here. Let's continue. 1 over 2 times mg over. Let's replace this force of the wall by friction force. So it's going to be mu times normal force. Okay? That is going to be equal to tangent theta. So now we can find the theta easily. Alright? So the normal force, remember the normal force was equal to mg. So let's replace it here, normal force as well. So the equation will turn like this: 1 over 2 mg over mu times mg equal to tangent theta. So mg, they're gonna simplify themselves. We know that our mu is given as 0.5, right? 0.5 is given. So it's gonna be tangent theta will be equal to 1 over 2 times 1 over 0.5. So when you multiply this two, it's going to be 1. So tangent theta is going to be 1. When tangent theta gets value of 1, when sine theta and cos theta have the same what do you say, degree, which is 45 degrees. So to find the theta, we're going to do like this: tangent 1. When you use your calculator, you're going to see that theta will be 45 degrees. So the answer will be 45 degrees for. So this question was an extra question for you guys. So the tangent force on the T1 we are gonna find. So let me draw it over here, actually, because I couldn't do it here. So there's a person over here. There is 1 meter distance over here. Totally, the length of the rod is 4 meters, right? Okay. So here the guy has how many Newton? It has 1,200 Newton. And our plank or metal rod, on the other hand, it has 1,000 Newton. Wait, okay. So since we are looking for T1, okay, so we are going to consider that our axis is here, okay? So this is going to be our axis because we are looking for T1. All right? So to find the T1, now let's apply it. So T1 times sine theta, theta is here 90 degrees, it also is 90 degrees. Times the length of the total length of the, what do you say, the plank over here, equal to, or let's say minus because as you see, the direction of the T and direction of the weights are in opposite direction. So minus the weight of the man times the distance of the man from T1, which is 1 meter, times sine theta, minus, let's continue, the weight of the plank times the distance from T1 to the plank, which is 2 meters, times, we don't need to use sine theta, that is going to be equal to 0, okay? So now, let's leave alone T1 sine theta out. T1 times sine theta, you know, sine 90 is already 1. So let's put it here 4 meters, the total length of the plank. So here, the weight of the man is 1,000 times, no, 1,200, sorry. 1,200 times 1 plus sine theta again is 90 degrees, so there is no need to put 90 over there, plus 1,200. Oh, sorry, this is 1,000. So 1,000 times, let's put it here, 2 meter plus minus, let's say, no, plus is going to be left hand on the other side of the equation. 1,200 times 1. Okay, so it's going to be 41 equal to 2,000 here, 1,200 over here is going to be 3,200 Newton. So here we are going to find the T1 as 3,200 over 4. That is going to be 800 Newton, okay, for T1. So what if you want to find the T2? Okay, what if you want to find the T2? What's going to happen? You want me to find the T2, you guys? So to find the T2, this time we are going to consider that this is going to be our axis, okay? So axis will be here. Rotation of the axis. Our rotation will start there. So to find the T2, again we are going to apply the same formula, T2 times sine theta times L minus the weight of the flank times the length, which is going to be L over 2, times sine theta, we don't need it actually. So minus 1,200 the weight of the man times this time is going to be the distance from man to T2. How many meters is it? 3 meters. So you have to get it 3 meters here, okay? So then, again, let's find the T2 sine theta equal to, let's say, 1,000 times 2 plus 1,200 times 3. Here T2 is going to be 4 T2 again. Is going to be equal to 2,000 plus 2,000 plus 300, 600, 3,600. That is going to be 5,600. Okay. So to find the T2, they're going to divide both parts by 4, and then they're going to get 1,400 Newton, the answer for T2. So the tension on T2 will be 1,400